As you can imagine, that was very dangerous because if you had a combustible amount of gas, the lamp was your ignition source. Eventually, we learned that using batteries and a screen mesh barrier to prevent flame propagation was the better way to do it, but that was still very crude. And then all of a sudden, microelectronics and computers took over, and now using things like a catalytic filament and other technologies, infrared, we've brought ourselves into the modern era of gas detection. Okay, so let's start off with just getting past some of the gas monitoring terms and a little bit about gas detection itself. We always like to bring into the picture all these terms because to do your job, to help assist the customer, you need to know gas detection well enough so that you can tell him what he needs and how to do his job. One of the things we always tell all our reps is you don't want to tell the customer where he needs gas detection, how he's to place his gas detection, how many points he needs, but you want to educate him so that he will be smart enough to put in a proper system. Now, of course, you can assist him, but again, from a liability point of view, you never really want to dictate and tell him what he needs. God forbid something happens, he's going to come back and say, well, you told me to put 2 sensors on the floor. And if it turns out to be the wrong position, you could be held liable. So let's talk about it. In our field, because we're doing both toxic and combustible gas detection, we need to understand the comparison between parts per million, percent by volume, and of course, when we talk about lower explosive limit, we're going to be talking about percent LEL. Parts per million is relatively easy. A good example is 5% by volume is equal to 50,000 ppm. One of the reasons why you should be fluent in this is because depending on the industry that you're talking to at a particular application, dictates whether or not they're talking in terms of ppm, or they're talking in terms of percent by volume, or they're talking in terms of percent LEL for combustibles. LEL, LFL. Typically in the United States, we use lower explosive levels, and this is strictly for combustible gases. LFL, lower flammable limit, is a term that's identical, except that that's more popular in Europe. And the real difference between the two, if anybody ever asks, is basically because if you ignite a flame in an open area, it's an explosive, a lower flammable limit. If you explode or ignite that same gas in a confined space, such as a container or a room, the pressure created by that flame is what creates the explosion and heat. And of course, then it's LEL, but basically they mean the same. Now, our most popular gas of concern, especially here in the States, is natural gas or methane, CH4. It's got a lower explosive limit of 5% by volume, which is 50,000 ppm. Comparatively, propane is 2.1 and butane is 1.9. So you can see every gas that has some type of explosion property has its own typical LEL. And that's why when we sell gas detection, we put it in terms of 0 to 100% LEL, because then one scale on every detector is good for any gas that you want to detect. And all you do is you change your range or resolution to accommodate that particular gas. We'll talk about that when we get into the actual applications. UEL, upper explosive level, is not necessarily important for gas detection, but good for understanding the dangers of gas. Upper explosive level basically tells me that for methane, it's 15, 16, about 16%, which means that between 5% of the lower flammable limit and 16% for the upper explosive limit, that is your danger zone. That's really the place where you don't want to be, and therefore using gas detection and monitoring for gas detection warns you way before you get to that 5% for methane. I gave you the other examples. Propane is 2.1. Propane UEL is 9.5. You can see it's a smaller window. And butane is 1.9 to 8.4. Every gas has its own LFL and UEL. Moving on, we always see the acronym CHC, and that's in our industry, that's considered combustible hydrocarbon. Now, when we start getting into actual chemicals, it's important to understand certain properties about those chemicals, because that's going to tell you a lot of information on where you're going to put the sensor, why you're going to put a sensor, whether you even need a sensor. Ignition temperature is probably one of the more important things. It's the lowest temperature at which combustion can take place, obviously when you have a ignition source. Methane is our standard, and the reason we use methane as a standard is because out of all the gases that we do detect, and we'll show you a list a little later on of all the ones that we've done up till now, methane is the highest ignition temperature. It's got an ignition temperature of 999 degrees Fahrenheit, which basically says if there's a cigarette butt that's at 500 degrees and you have a methane and oxygen mixture, that cigarette cannot ignite methane. So you don't really have to worry. I mean, I still worry, but you shouldn't have to worry about an explosion. Now, on the other hand, if you have gasoline and you have a 500 degree ignition source in an oxygen environment, you have a potential of igniting the gasoline vapors. And hydrogen is 932, and that's very important, as we'll discuss a little later. So every gas or vapor has a specific ignition temperature which needs to be identified when you're setting up or installing a gas detection system. The flash point, the temperature which a compound can ignite in air, is also very, very important in gas detection. Isopropyl alcohol, for example, at 65 degrees Fahrenheit becomes flammable. So all of you East Coasters, actually most of the country for that matter, in the last 2 weeks, if you had a container of IPA, it probably was safe because the temperature outside was so cold that you couldn't have enough vapors being given off by that compound to ignite. Whereas difference with gasoline, and the reason why gasoline burns so well even in a car engine at low temperatures, is because its flash point is minus 45. So as long as it's above minus 45 degrees Fahrenheit, gasoline vapors are dangerous. The third one I give as an example is I basically give because we've had some applications out there where customers have called us and said they need a gas detection system for ethylene glycol. They have, especially in the old days when that was used in the antifreezes, and in a lot of cases it still is, although propylene glycol is used more often now. Ethylene glycol's ignition temperature is 232 degrees Fahrenheit. What that basically means to me is that in room temperature, if you're storing this in an open vat, you really have no worry that an ignition source is going to ignite that ethylene glycol vapor, because it's just not high enough or hot enough to give off enough vapors called the flash point. Therefore, he really didn't need, the customer who called me really didn't need gas detection. However, OSHA came in and said you have to monitor for combustible hydrocarbon because ethylene glycol is flammable. Well, yes, it is flammable at 232, but not at room temperature. The customer really had no choice because to meet OSHA's requirements, he had to put a gas detection system in for his ethylene glycol vat. Okay. Okay, moving on to vapor pressure for liquids. Basically, vapor pressure is important because by looking at that number, and it's not the only number you can look at, but by looking at that number, you can determine whether or not you have a liquid that is going to be a little bit dangerous, very dangerous or not dangerous at all by its evaporation rate. As you can see, acetone, and everybody's familiar with acetone, it used to be used in nail polish remover, and it's a good solvent. That has a 30 psi vapor pressure compared to water, which is 2.4. And we all know that water evaporates. If if you look out on a summer day and after it rains, the water disappears within an hour because it's evaporating. Acetone evaporates much quicker, and therefore you would guess that a particle of acetone or a leak of acetone would immediately go into a vapor phase and meet that flash point and then become very, very flammable. Vapor density is also a good thing to know because that will tell you where you want to place your sensor. Now you can do it in two ways, vapor density or molecular weight. If you're looking at vapor density, unless you're a chemist and into that stuff, the numbers become very confusing. I particularly like, because it's so much easier, to use molecular weight to determine where I want to place my sensor, because it's very easy to me. You can actually calculate that very easy by looking at a periodic table. Air is considered to be 29 molecular weight, where propane is 44, and carbon monoxide is 28. So if I was putting, let's say I was putting a gas detection system in maybe a garage that also had propane-driven buses, I would have to know that air being 29, I need some sensors at the floor because 44 is 1.6 times heavier than air. And carbon monoxide, I probably want to put those sensors at the ceiling because it's slightly lighter than air. And of course, coming out of an engine being hot, we all know hot air rises as well. So carbon monoxide probably should be detected at the ceiling. So that's how you can determine that molecular weight is a good way of determining where to place the sensors. When we get into toxic sensors, such as electrochemical systems, we need to know a little bit about the toxicity of a particular chemical or vapor. The three groups that we use here in the United States is OSHA, NIOSH, and the ACGIH, American Conference of Governmental Industrial Hygienists. The three things that we're concerned about is a TWA, time-weighted average, which basically says how long can a worker work in an environment over an 8-hour period, a typical work day. Then we have to say, what's the cell? What's the ceiling? What can he work in an environment for a 15-minute period? And then, of course, the real thing that we want to know is what will kill him? What's the IDLH, immediate danger to life? And that's the maximum that anybody can wolf in one breath that might kill them. Okay, so typically when we do toxic systems, and that's going to be in parts per million, we're going to worry about two things. We're going to worry about the time-weighted average, okay, how long that worker can be in during a normal working procedure, or maybe the ceiling. What's the highest he can, if you go into a room to go get some chemical, but you're only walking in and walking out, the cell might be more important to that application. So now we start looking at combustibles. Okay, so our biggest market, and possibly for you too, is going to be the combustible market with many different chemicals in many different niche markets, whether it be 1 or 2 points in a strip mall because of methane over a landfill, or whether it be in a Huntsman, a Goodyear, a Dow Chemical, where they have multiple different chemicals that are considered hazardous. The example I use here is for methane because it's the simplest and most common. And what we see here, as I explained earlier, 5 to 16% is the explosive mixture. What we're concerned in gas monitoring is below that 5%. We want an early warning system, and we want to know it well before it becomes 5%. So we'll have a 0 to 100% LEL scale. We'll probably set the alarms to 20, 40, 20 low, 40 high, or maybe 15 low, 25 high. That's dependent on your internal safety of the particular plant that you're installing this at. A couple of, when we started out back in the well, Delphian started out in, I think, 1974, but in the early 70s and 80s, there was no internet. And therefore, the Bible used to be the NFPA 325M handbook, where you can get all the information in one book and be able to determine the properties of a specific gas. On this one, I took the page out for methane, showing that it is a gas, so it's a flash point. It doesn't exist because there is a flash point way, way below anything that needs to be reported. We see the ignition temperature of 999. We see the lower of 5 and the upper of 15. Depending on what book you look at, the upper is somewhere between 15 and 16. So sometimes I show it as 16, and that's really in the direction of safety. So as long as you're above 16, you're okay. As long as you're below 16, you're probably in the danger level. It also shows you the vapor density, the boiling point, and all that stuff. So this was a great book. Well, now with the internet there, Google has become my best friend. I can go on within seconds, call up a specific gas such as cyclohexane, and I could type in cyclohexane SDS, and I come up with a whole safety data sheet that tells me all the properties and hazards of cyclohexane. So this is a good book or a hardcover that you could use if you want something in your office. But like I said, in most cases today, you go right to the internet. We get into also, when we spec out a gas detection system, we also get into the NEC hazardous area classification codes. And for combustible gases, we're really talking about a class 1 for flammable gases and vapors. We do have some hazards from explosion and fires from dusts, but we don't have any product that detects for dusts or powders or something to that effect. So we're basically a class 1. In class 1, there are 2 divisions. There's division 1, there's division 2. From Delphian's point of view, we don't really care from a product point of view, because all our equipment that we sell is sold for class 1, division 1. And that means you can put it in a division 2 and it'll work just as well. The real difference between those two is division 1, you expect gas or vapor in a dangerous level to be there as a daily, possibly a production cycle. Division 2 is maybe storing some tanks. You don't expect them to leak. You don't expect the gas to be in the area. But if something does happen because you're storing liquids and gases, you need gas detection to make sure that you don't create the explosion. So most of our sales is done in class 1, division 1. In the group area is basically designed to tell the manufacturers really how well they need to build their equipment. And very simply, a group A, acetylene, when exploded or ignited, produces the most pressure, the most flame, the most ignition pressure of all the gases. Group B, being hydrogen, butadiene, so on and so on, is a little less. Group C, again, a little less. And then there's Group D, which is your natural gas, your methane, your butanes, acetone. And basically what that's telling you is that if I was to put a stoichiometric mixture of those chemicals in an enclosure with oxygen, stoichiometric mixture, and ignite it, I would get a certain pressure on a gauge that we'd have to design that equipment to make sure that our equipment doesn't bend, stress, crack, or blow up under that pressure. And of course, like I said, as you go up the scale from D to C to B to A, the pressures get higher. So most of our equipment is, we have some the determinator IRs of group B, C, D. The gas tell, all the gas tells are group C and D because of the type of gases that we're monitoring. The last thing we should know about the basics of installing a gas detection system is what type of enclosure these things or equipment are put in. Now, of course, I left some of these things out just so it would fit on the slide, but there are typically 13 different types of enclosures. The ones that Delphian and most of our competition use is NEMA type 12, which is just a enclosure to make sure that people don't touch the PC board and is oil-tight, industrial use, but not necessarily explosion-proof or protects from water or corrosion. When you get into the explosion-proof hazardous line, we're talking strictly type 7. That's all our equipment is made to type 7. And we've added a 4X rating on it because we epoxy coat all our aluminum housings, and we seal them either by O-ring or by tightness, and that makes it dust tight and corrosion resistant and watertight as well. So almost everything that Delphian sells is a type 7 and 4X. Okay, let's talk about the sensors and their technologies. Right now, there are probably 2 or 3 new technologies out in the market that really haven't come to fruition yet, but the 4 basic ones that almost everybody, including Delphian, use at this time is electrochemical, catalytic, infrared, and semiconductor. Okay, the electrochemical sensor is an electrochemical cell. We now sell the Gastel 450 model 455, and that's an electrochemical instrument. Catalytic bead sensors, we actually have 2. One is not on the market yet. Everybody's familiar with the 550 common sensor and the 550 system, but we also will be introducing shortly, it's right now at FM Factory Mutual being tested, and we hope within the next several months we'll get the approval on that. That's the model 470 Gastel CHC, which is the catalytic bead. Infrared, we've had out for probably 17 years now, which is the determinator and the remediator. But we've also recently, in the last 6 to 8 months, introduced the model 450 Gastel IR. And we'll talk about a little bit about the differences between both of them. They both use infrared technology, but they are very different, and we'll describe that later. Semiconductors. A lot of people use semiconductors. American Gas and Chemical, which is our sister company to Delphian, uses the semiconductor sensor. We sell it, the reason we don't sell it under Delphian is because we think of it more as a go, no-go gas monitor rather than gas detection. So I want to say it's sloppy. It changes drastically over temperature and humidity. So from a go, no-go instrument, yeah, do you have a leak or don't you have a leak, it works great. If you want to know the exactness of your leak, it's not probably the technology that you want to use. And we'll talk about that. I'll show you the instrument that we actually sell under American Gas, which is available for you guys to sell as well. I believe you can buy it and get 25% off the list, and then you can sell it for whatever you want and make your commission that way. Okay, so let's talk about electrochemical sensors. They were designed, the beautiful thing about NASA is that there are so many great things that came out of NASA, including computers, because of its need to miniaturize and improve and get all these neat technologies that we needed to get ourselves to the moon and Mars and beyond. So NASA helped us in pushing us to design technology that we can now sell in the normal market. Basically, a electrochemical cell is like a battery cell, okay, except that it works opposite. It contains electrolyte, and it has sometimes whether 2 to 3 electrodes within it. It has a little membrane that prevents the electrolyte from oozing out of the cell, but allows gas to permeate across it. And the way it works is almost the opposite of a battery, where in a battery, we charge the electrolyte so that you can get free-flowing electrons out of the battery. An electrochemical cell is opposite. We have electrolyte that's not charged. And when gas comes across the membrane and then goes into the cell. We then have a chemical reaction take place, and we don't have to get too much in depth of the chemical reaction, although I gave you one for carbon monoxide there. We basically wind up with the gas mixing with the electrolyte to produce a free electron, and that free electron can flow from cathode to anode, producing a current. The more gas that flows into the cell, the more free electrons are produced, the higher the current. And it's a very simple thing. The disadvantage of electrochemical cells is that the more gas it sees, the more it consumes the electrolyte, and the quicker it dies. Sort of like a battery. If you take a battery and you put it in your desk drawer for 10 years, you probably have a flashlight that works after 10 years. If you use a flashlight every day for a half hour a day, that battery will only last you a month or so. So the more you use it, the quicker it gets consumed. The other thing is there are some interfering gases that could affect an electrochemical cell. So you have to be very aware of other gases or vapors in your environment that might affect or give you false alarms when using electrochemical technology. It is very specific, or can be very specific, and that's the beauty of an electrochemical over a more generic, well, we talked about the solid state sensors. Solid state sensors pretty much see a whole slew of different chemicals and vapors, where electrochemical cells have been sort of focused on one or two specific chemicals or groups, such as sulfurs like hydrogen sulfide and the sulfur group. Almost all electrochemical cells detect in the part per million range. The reason, very simple, is because it's typically a safety device. You put it in a lab, a room, a parking garage, and you want to know when a certain level is achieved that meets the TWA, time weighted average, or the ceiling, or the IDLH, immediate health hazards to life. Okay, so ppm is typically what they talk about when you're talking about electrochemical sensors. The one exception is an oxygen electrochemical cell. Okay, oxygen we're all familiar with in terms of 21%, what was it, 20.9% oxygen in air at sea level is typical, and therefore we talk about oxygen in percent by volume. Okay, a typical oxygen sensor will show you 0 to 25% by volume in a specific application. So it's more used, it's mostly used for oxygen deprivation or enrichment applications. So you want to know when you can go into a room that has enough oxygen for you to breathe. So electrochemical, okay, what do we have to offer? We have new electrochemical cells, which are state-of-the-art, all digital, and we do that with a electrochemical gas cell, which is both toxic and oxygen. And as you can see, it's a very small unit. It's only about 5 inches tall by 2 inches wide. It's very power. It uses very small amounts of power, so it's now more applicable to applications such as offshore drilling rigs or places where you have battery backup systems, and therefore the less power, the longer the battery backup system will last on offshore rigs, the less power you have to generate at a cost savings. The beauty of these things is the electronics itself. We have a mean time between failures of over 8 years. In the IR group of gas cell, we know that these things are lasting 12 to 15 years out in the real world. So they've got some good history. It has a nice LED display. The warranty on it is 1 year, 2 years for the actual, 2 years for the detector and 1 year for the actual cell. Right now we have electrochemical for ammonia, carbon monoxide, chlorine, ethylene oxide, hydrogen cyanide, hydrogen sulfide, nitrogen dioxide, sulfur dioxide, and of course oxygen. Rob reminded me, we just did a couple of systems for mercaptan. In all fairness, as I told you, the mercaptans are in the sulfur group with hydrogen sulfide. So basically, you can do a lot of the different sulfides using the hydrogen sulfide cell. So we've done some mercaptans, and of course, for those of you who don't know, mercaptan is used in the pumping transmission of natural gas because they use mercaptans to odorize the natural gas or methane that has no odor, and therefore by odorizing it, they've injected into the whole system a safety feature that when you smell the mercaptan, you must know that there's a gas leak somewhere. The gas cell, again, being a very new and unique type system, not only is cheaper than most of the other competitor systems out there, significantly cheaper, but it has some accessory modules that you only have to buy if you need it. Excuse me. Okay, it was a great song, but that was my wife. The gas cell modules are a great option to the gas cell detector head that are used only when required. Different than a lot of our competition, where you'll buy a competitor's unit, it has relays in it, it has all these other options in it that you don't really need, but you're paying for. So if somebody needs a sensor mounted up in a ceiling and therefore can't see that sensor and wants to see the results or the display at room level or eye level and wants to calibrate at the room rather than getting a ladder and going up to the ceiling, you would add the XMO, which is the extension module. And basically what that does is it mimics identically the detector up in the ceiling. So whatever the detector is showing, the XMO is showing as well. And it mimics the 5 different or 6 different magnetic Hall effect switch actuations that you can do. So you can take it offline, you can calibrate, put it in calibration mode, you can reset the SLAM, all from the gas cell XMO. The SLAM is the last module, or the third module in the series, which is just a relay module. So if you want to put that 20 feet away or up in the ceiling or somewhere near the horn, light, emergency solenoid shutdown device, it is a module that you can set for whatever levels you want. We have a low alarm and a high alarm, and you can put that wherever you want. So again, if you don't need relays because you're sending this back to a PLC, then you don't need to buy a SLAM, and it saves you some money. The price, by the way, is probably cheaper than any of the competitors that I've seen on the market with similar products. So Rob can talk to you about that in more detail. I'm sure most of you by now have the price list. Okay, so let's go into catalytic bead. Catalytic bead sensor has been around probably since the 40s and 50s. It started in the 30s, but really didn't come into its own until we started having some good electronics that made the cost worth buying. As everybody remembers, you know, when you had the first processor chip, it was $1,000 for a processor chip, and now they're in your watches, your iPhones, and they're probably 50 cents. So technology, as it's evolved, has made these things much cheaper and much easier to afford. Catalytic bead is based on catalytic reaction, okay? The fact that when it burns, it is not consumed, but it allows the reaction to take place at lower temperatures so that you don't necessarily have to have an ignition for the reaction to take place. I'm hoping, let me see if I can get my cursor. I hear one voice on there. Can you see my cursor moving around? Anybody out there that can see that?
Yeah, I can see it.
Thank you. Okay, so the way it works is you design a sensor with a platinum surface. Okay, so this is the sponge coating that allows the reaction of methane in air to ignite or burn at the surface of the bead, and this ignition produces as a byproduct heat. And when heat is detected, when heat is detected, we can then use an electronic circuit to detect that heat. I don't know why this keeps going back and forth, but so typically catalytic beads are put into what we call a Wheatstone bridge. Okay, and the Wheatstone bridge. Okay, a Wheatstone bridge is a circuit that basically uses a reference and an active bead in that circuit. And the purpose of that is that when the guest is exposed to the sensor, only the active bead will burn the gas, and the reference bead stays stable. And again, the purpose of this is designed basically because we want a catalytic bead to be able to perform well throughout a very wide temperature range. In the case of Delphian's catalytic bead, we can go from minus 67 degrees Fahrenheit all the way up to about 300 degrees Fahrenheit. Therefore, it makes it very viable for a whole slew of different applications where temperature is an issue. The actual catalytic beads last about 2 to 4 years. Obviously, the cleaner the environment, the longer the sensor will last. It is also specific to combustible gases, but we can sort of tune sometimes the catalytic bead for a specific group, such as hydrogen, for example. If we wanted to use a catalytic bead sensor for hydrogen and we didn't want it to see some other gases such as methane, we could lower the temperature of the bead, operating temperature of the bead, and therefore allow it to see one and not the other. The big disadvantage of catalytic beads, and this is why infrared became so popular, is that catalytic beads get poisoned pretty easily with things such as halogenated hydrocarbons and silicones. Also metal organic compounds such as lead and gold, and but you don't normally see that anymore. In the old days, the tetrahedral lead, which was used in gasoline, poisoned the sensor pretty quickly. But silicones and halogenated compounds really are their enemy. So you can't run a catalytic bead anywhere around silicone-based materials or things like fluorine and chlorine molecules that might be in propellants, for example, refrigerants. So we have used catalytic bead in an environment that had air conditioning systems, halon dumps, for example. If you use a catalytic bead in a room that's monitoring for some combustible gas, and you have a halide system that dumps on a case of a low alarm or high alarm, one of the problems with that is that the halide dump will also kill the catalytic bead. So you probably have to replace the bead after the alarm goes off. As far as catalytic beads, a couple of things you should know about sensor technology is that the catalytic bead itself is dependent, its response time is dependent on concentration. So I put a couple of graphs in here that show that, because that is a common question that I often see out in the field, is how quickly they'll respond. Now, besides the mechanical properties of a sensor, when the gas gets into the bead, and I'm probably going to say that 95% of the speed of response is because of two things: the actual mechanical capability of diffusion of the gas into the sense chamber, and the actual amount of heat that's produced by a particular gas concentration. So this first graph I show you is 100% LEL, okay? And you can see that if I wanted to go to a 20% alarm, it would be about a little under 3 seconds before I actually got an alarm on that sensor. Now, if I had a full blowout of a valve where you got 100% by volume almost instantaneously, then what you would see is a 20% alarm would be in about 1.5 to 1 3/4 seconds. So you can see the concentration is very important in determining how quickly the response time of catalytic bead sensor. Delphian's product line consists of two different products. Right now, what everybody there, whether you're longtime reps or you're new, the 550 common sensor is the device that we use for catalytic bead since I'm going to say 1976. Of course, we've gone through many iterations of its design, and now we've come up with what we call the common sensor, which is a replaceable element sensor. So instead of, in the old days, you used to buy a sensor. When it burnt out, you used to have to replace the whole sensor. Now we can sell you what we call an SB, an element sensor bead, in a replacement PC board that plugs into the sensor. So you remove the flame arrestor, you plug in a new element, you do a quick coating resistor on the back of the sensor. That's the setup to make sure that it's running at its proper operating temperature. And you have another sensor, and that replacement element is about $90 compared to $222 for the entire sensor. So in many cases, we've saved companies by 60%. We've giving them savings of 60% by actually allowing them to replace the elements rather than replacing the whole bead. Also in this picture, you'll notice that we have a foam splash guard. That is a device that Delphian has come up with. It's a patented proprietary device. It's a reticulated foam that goes over all our sensors, that protects the sensor from rain, wind, dirt, paint, ice, and it's a real nice way of making your sensor last longer. Okay, that's catalytic bead. Let's go into infrared technology. Infrared's a little different in the way it works because it has nothing to do with combustion. Infrared technology is all about light and light absorption. I could probably talk about 3 hours just on this subject because it's such an interesting physics on how it works. But for those of you who don't know, the human eye can only see the rainbow colors from purple or violet all the way to all the way to red. Once it goes past red, it goes into the infrared zone, and there are near, middle, and far infrared wavelengths. The property that we're concerned about, or the area that we're concerned about, is due to the fact that carbon molecule vibrates at a very specific wavelength, a very specific energy level. That's between 3 and 4. Actually, more specific, between 3.2 and 3.4. And what that means is that that energy of light, when it hits a carbon molecule, and that carbon molecule starts to vibrate, it's using up energy when it vibrates, and that light wavelength is absorbed. Therefore, if you were trying to look at a carbon molecule using light, you could come up with the conclusion that when that light disappears for some reason, there must be something in the way of that light absorbing it, so the detector cannot no longer see that wavelength of light. The way Delphian does it is with the determinator especially, and the remediator, but specifically the determinator, is we have created a optical tube coated with gold, and gold reflects IR light most efficiently compared to all other metals and surfaces. So what we have done is we've come up with a method, okay, that allows a detector on one end and a light source on the other. The light source outputs what we call a white light. It's a broad spectrum of frequency, light frequency, that hits your detectors. And those detectors are set up with a filter to see a specific wavelength. On a single IR detector, let's use an example of 3.3 microns. When the light source hits that detector, it sees a very large amount of light. That is depicted by the graph on the lower left, which says when my light is on, I see a lot of light, and then when the light goes out, I see no light, and on and off and on and off. And that happens 0.8 seconds each cycle. And what that means is that over time, the IR detector is looking at the light on, light off, and determining where that absorption of light is. Now, on the right side, we introduce methane, and that comes in through the bottom of the optical tube, and then because of heat, this is a heater, and that heater produces a chimney effect, which allows the hot molecules to rise and escape. And then we just keep getting this circle of diffusion, which allows methane to go into the optical tube. Now, one of the things that happens is, as I said before, the carbon molecule in CH4, that carbon molecule absorbs light in 3.3 wavelength. Therefore, that light that's coming out from the source, going up to the detector, is now, that methane molecule is absorbing some of that light, so that the light energy doesn't see as much as if the light was on with no methane compared to the light on with methane. So what we wind up doing is, you compare these two graphs, is you can see now light on is some light energy absorbed, light off is still the same, light on, light off. And now we have a method of determining how much gas is in the tube depending on the absorption of light. And that's the simplicity of an IR detector. The complications are enormous, okay? When we design this thing, we probably have 30 or 40 algorithms that have to be put in to compensate for moisture, that have to be compensated for temperature, atmospheric conditions, change in light source, change in detector failure over time. So all these things are determined up front. We have been very successful with the determinator in the sense that we have determinators out there that are probably approaching 15 years and still working perfectly. The MTBF, we've calculated out to be about 8 years, so the mean time between failures is about 8 years. But we have IR detectors that last, again, typically 8 to 12 years. And that's a big improvement when you think about comparing it to a catalytic bead. So if you were to put an IR in for methane compared to a catalytic bead for methane, every 2 to 3 years you'd have to replace the sensor, and you'd have to maintain it by calibrating it every 30 days. The infrared you calibrate once a year, and you don't have to touch that sensor for 8 to possibly up to 15 years. So maintenance is cheaper, and the cost of the unit over the long period of time is cheaper. And of course, the price isn't that much different. So I think up to years ago, a base catalytic based system was probably $1,100–1,200, where the IR is about a $1,500–1,600 item. So they weren't that different where you just couldn't afford to put IR in. So again, there's no consumable components, there's no mirrors, which was one of the early problems with IRs, because a lot of our competitors used mirrors to reflect the light from the light source to the detector. We actually use an optical chamber, gold-plated, gold flash, 25-carat gold flash, and therefore there's no mirrors. We also use a heater on the optical chamber to do two things. It prevents condensation because it's warmer than the atmosphere, and also it creates the chimney effect, which allows the gas to be almost pushed or pulled through the chamber. And of course, the best thing out of all these things is that span is not required on a normal basis. Or, in fact, with the determinator, it doesn't have to be ever calibrated, okay? And the way we do that is very unique, which I'm going to explain a little bit. Okay, so in the determinator, first of all, let me tell you this. The determinator is a 4-detector IR detector unit. What that means is we use one channel for a reference channel and 3 active channels. And what that tells you is that we actually are looking at 3 different wavelengths of light. We are the only ones in the world that I believe do this. All our competition uses 1 or 2 channels, and they could only see 1 gas at a time, or 1 gas in a application. So if a customer comes to them and says, I have methane, propane, and butane tanks, and I'd like to monitor it, they're typically going to say you either need 3 IRs, or you can't do it with an IR, you need a catalytic feed. Where Delphian can actually say, we can set up 3 different IRs for those 3 different gases, and when you have a leak, we can identify what gases it is, and all 3 IRs can give you a response that's accurate for any one of those 3 gases. And the way we do that is, again, we have 3 channels of detection. Okay, there's 3 detectors with 3 different wavelengths. And what that does is, I'm trying to get my cursor back here. You can see there's a short wavelength, a medium wavelength, and a long wavelength. And when you hit it with 10% LEL, 25%, 50, 75, 100, 200, and 500, we can actually get and give you a graph of the response of those 3 detectors. Now you can see this one channel here is our reference channel. That will never change with gas. The only time that changes if it sees moisture. So that we use that channel as our moisture detector. This is for methane. If I quickly go over to ethane, you can see that ethane hardly has any absorption in the short range, but it does in the medium and the long. So those 2, if you look at the difference between those 2 graphs, you can see there's a very easy way for me using software to say, hey, I can tell the difference between ethane and methane. And in fact, I've done this one, which is a little different. I've graphed it in a way that shows you what we call the fingerprint. So in infrared, when you have 3 channels and you can, in the laboratory, come up and say, what are those absorption rates for those 3 different channels for a specific gas, you can come up with a signature, or what we call here is a fingerprint, that allows you to see the difference between gases. Now on the top you see in red, you can see that methane has absorption in all 3 channels, but a little different absorption rate. Butane, however, has very little in the 3.2, some in the 3.3, and a lot in the 3.4. If you go to gasoline, it's almost opposite. So looking at the fingerprints during detection and software, we can come up and say, when we see the green fingerprint, we know it's gasoline, and we're going to tell you using the processor display that you have a gas equal sign 080 equal sign. That's your identification number. Obviously, if you bought an IR for gasoline, you would be told what that gas number is, and therefore when you saw it display 80, you would know that that's gasoline compared to 12 or 1, which is butane and methane. So it's a very unique, we're the only ones who do it, and what that allows us to do is it allows us to load these lookup tables into the sensor head when you purchase the sensor. So if you need methane, butane, gasoline, and acetone, we can load those 4 chemicals into a head, into one head, and that one head can then monitor 4 different gases in one head. And that's the beauty of the determinator. Now we can do up to 5 gases. So once it gets past that, even though we can do it, we don't recommend it because it gets too messy, because when you start overlapping a lot of chemicals, these fingerprints might overlap in ways that might not be able to be identifiable by the detector. Up to today, we actually this has changed, but it's pretty close. These are the chemicals we've actually done using a determinator IR. A lot of you guys have been around for a while, probably have can have identified your gas down in Houston, tetrahydrofuran. We have the butadiene, so those are very common chemicals down there. Out in California, methane right now is our biggest product out there because of the tar pits and all the methane oozing out of the ground in the Los Angeles County area. Throughout the country, one of the popular sites right now is landfills. We sell a lot of systems to, we installed one at a Hilton Homewood Suites, a Federal Express building. We've done Petco, we've done Lowe's, we've done Costco. So they're out there. Any building that's put on a landfill is mandated that they have to have gas detection. So that's become a big market for us. Continuing on the IR journey, our new product, GasTel Infrared. Okay. Now, immediately I don't hear it, but I know what you're asking is, why do you have two? Well, we have two for two good reasons. Number one is the determinator, again, does multiple gases, and we're the only ones in the world that I know that do that. So if you have a customer with 2, 3 gases or 4 gases or whatever, the IR determinator might be the way to go. And it's pricier. It's twice the price of a GasTel. Again, the GasTel being a smaller single detector head, so it has a 2 detector head detector, which is one for reference and one for active channel in the 3.3 range. Of course, it's going to be cheaper. It's smaller, it's cheaper, it's less power, but it has exactly the same accuracies and longevity as the determinator. So although this is a brand new product that's only been out for a little less than a year, we know that it's a great technology and it's going to be very reliable, because we're using basically the same thing that's in the determinator, except that we took the 2 or 3 extra detector heads out of it. It also has an MTBF of 8 years, warranty of 2 years. It's good for operating from -40 to 70 C, and its power is a little wider than the determinator. We can go from 12 all the way up to 42. We're thinking that sometime in the future that automotive industry might go to 42 volts rather than a 12 or 24 volt battery. So we've accommodated this unit to be able to be put in that market. Okay, we move on to semiconductor. As we talked about earlier, the 4 different technologies: electrochemical, catalytic bead, IR, and semiconductor. Semiconductor is not my favorite at all. The reason is because it's really, in my mind, a go, no-go type device. Now, if you're putting it in an area that fits that niche, it's a great device. A good example is we've had schools put it in boiler rooms where they just mount it in the boiler room. They never have to touch it, and this unit will last them 20, 25 years without changing the sensor. We put it in hospitals for ethylene oxide. We put it in parking garages, heated parking garages specifically, that looking for carbon monoxide. So it has its niche market, but the disadvantages, again, is that as temperature changes and as humidity changes, it's not very accurate. I would say it's probably a 10 to 20% accurate unit. So if you're using it as a go, no go, yes, there is gas, no, there isn't, it's a perfect unit for the application. We sell that in what we call the SBG 200G, which is a wall-mounted unit. You buy it for a specific trigger of a chemical. So you might come over and say, I want it for methylene chloride at 20 parts per million. We set it up in an environmental chamber here in our plant. We send it to you, you plug it in, you hang it on the wall, and you're good to go. So it's a very simple, it's an ANEMA 12 enclosure, so it's not explosion proof, it's not corrosion resistant, it's not airtight, dust tight. It's just a unit that I actually have, the original one that we designed. I actually have it in my my laundry room at home, monitoring for my boiler for methane, or my hot water heater for methane, or carbon monoxide or carbon dioxide if my flue should clog and back up. So it's a great unit. And again, this is sold by American Gas and Chemical. Okay, the Delphian design. One of the things we love and we tout our design on is its flexibility. We've designed all the instruments to either be standalone units or part of a more complex system. And because the market that we have varies from big petrochemical plants all the way down to Joe's barbershop in a strip mall, we have the diversity of selling the customer what he needs rather than what we want to sell him. And if he needs something simple, we'll sell him simple. If he needs something complex, we can go all the way up to a computerized-based Sage CE system. As you can see on here, from left to right, we have the 850 system, which is the Terminator infrared, which is also the 850 model, which is the remediator, which is for 0 to 100% by volume. We have the 550 catalytic bead with the safe cal. We have the 450 model gas cell, 470 gas cell, which again is coming out as soon as FM gets off their horse and gives us the performance rate approval. And then we have the 455 model electrochem. And any one of these can be connected to Delphian's FlexiRack system, which you see on the top is a wall mount, also can be put into an enclosure. And the one you see there is a digital unit. We also continue to sell the panel mounts, which can go right into a panel or a rack, a 19-inch rack. And that's what you see there are the analog modules. So we have both digital and analog meter variations on the FlexiRack and controllers. The next thing down is the Sage CE with its satellites. The beauty of that is it's sort of high tech. It's a HMI SCADA type system that is now being used everywhere in the industry for production and monitoring. And that uses what we call a data highway. So instead of wiring each individual sensor all the way thousands of feet back to a central system, you just put out into the field a twisted pair data highway, an RS-45 data highway, that now you can tag little satellites. And the satellite, if I get my cursor back up here again, there it is. This satellite is both a sensor satellite or a relay satellite that can be put anywhere on the line out in the field once that data highway is laid out. And the beauty of that is now sensors only have to be wired 50 feet or 100 feet to the satellite, and then that data highway can go back thousands of feet, up to 10,000 feet, back to the computer system, which cuts your wiring costs about 80%. So a system, a good example might be a 50-point system. If you do it with analog wiring, it probably costs you about $200,000 in wiring. If you do it using a data highway system, that same 50-point system might cost you $30,000. So you can see you save quite a bit. And of course, any one of these units can then just be attached directly using a 4 to 20 output to a PLC or DCS or to somebody else's system if they want to just change the sensors out. Okay, let's talk about sensor site selection, because this is going to be sort of the important thing from a sales point of view. As I had mentioned earlier, you never really want to tell the customer where to put a sensor, how many sensors to put in, and give him all that information. What you want to do is you want to teach him how to make his own decision so that he can basically take the liability and understand the do's and don'ts of gas detection. So the first thing we're going to talk about is accessibility. This is one of, well, they're all important, but this is sort of my pet peeve, because in early years when I went out to a lot of locations, what I found was the most frustrating is when customers installed sensors and systems in places that they didn't do it correctly. I've been to Dow chemical sites where they put sensors. If you look at that picture in the middle, they had a round sphere and they put a sensor right smack underneath the bottom of that that sphere, which had about 6 inches of space under it. And basically they had to crawl and get underneath that to do calibration and repair, and it just didn't make sense to me. I did another one all the way over to the right there. A guy put a non-explosion proof camera up on a flagpole, and they put a sensor up at the top of the flagpole. And the idea was that if the sensor found a considerable amount of gas, a low or high alarm level of gas present, then they would switch the cameras off so that the cameras weren't the ignition source for their explosion. The problem with that is that if you don't use the right accessories and you put the sensor up at the top of the flagpole, he only calibrated that system once a year because he had to rent a cherry picker to get to that sensor. Whereas now, such as the device such as the gas cell, you can put the sensor at the top of the pole, you put the XMO at floor level, you put a tube that runs up to the sensor with a ported adapter, and now you do all your calibration and gas testing from floor level. So we have accessories that make it easier, but you need to know where to put the right place to put a sensor to make everybody's job easier. Vapor density. We talked about this early on when we were giving you the terms. Lighter than gases, you want to put above the leak source. Things like propane, you want to put below. So using good physics and judgment, you can tell the customer, basically you can tell the customer what his molecular weight of his chemical is. And in all fairness, other than ethylene and methane, every other gas is going to be heavier than air and carbon monoxide. But every other gas, your propanes, your cyclohexanes, tetrahydrofuran, all those benzenes, they're all going to be heavier. So most likely, most of your sensors are going to be at floor or below the ignition leak source level. The other thing you got to also remember is air currents can create problems. So, and we actually have a slide for that. So air currents, and again, I took these pictures off the internet, but my point is that you always have to be aware of where your air currents are, because if you put a sensor, I'll give you an example. We had a customer put a sensor in the bottom of an elevator shaft for carbon monoxide. And the problem I had with that is it was a tall building. And if you've ever stood by an elevator in a tall building, the chimney effect, the flow of air is so high up that elevator that that's a waste of a sensor, because even if you had carbon monoxide going into that elevator shaft, the turnover of air is so high that that sensor would never see concentrations that can give you an alarm. So that would be a poor place to put a sensor, in my opinion. Now, if you could find a spot in an area or a house or a building that the air is static, that there's hardly any movement, well, that's a better place to put it, because that's most likely the area that's going to build up concentrations of gases. Okay, and of course, we talked about I show you a picture of the weather vane there. You have to be aware that the direction of the wind and the speed of the wind is also very important, because that's just going to dilute or change the direction of your the air currents, and therefore your sensor may never be hit with the gas that's leaking at all. Every sensor that we design, every sensor that a competitor has, all has temperature limitations, and those limitations are specific to a specific product, such as ours compared to a competitor's. It's also specific to the technology. You can't put an IR sensor in a 300-degree environment. You can put a catalytic bead in there, but not the IR. You can't, if you get down to, let's say, 60 degrees C, you can't put an electrochemical cell in that environment. It'll boil the electrolyte off. So a lot of the decision making on where you place the sensor is dependent on what the capability of that technology, also that detector head. It's values that are allowed to be used. And in fact, if you look on the labeling before, we talked about electrochem versus the IR, their temperatures are quite different when you talk about the technologies. Sensor orientation. Here's an interesting one, because the rule of thumb is you always point the sensor down. And that's for two different reasons. It's for mechanically, facing it down prevents dirt, dust, wind, rain from going into the flame arrestor and killing your sensor. Physically, there are reasons why that works, because on a catalytic bead, orientation is very important, because if you put the reference bead higher than the active bead, you got heat convection, which is going to change the values of those two beads. And remember, it's in a Wheatstone bridge, and if you change those values other than with gas, you're going to get some erroneous readings. So pointing down is the best position. With an infrared detector, we talked about a chimney effect on the chamber. If you turn that sideways, you no longer have a chimney effect, and therefore the rate at which the turnover of air through that chamber happens is going to be much slower. So your speed of response is going to be a little slower. So rule of thumb, you always want to put the sensor facing down. Now, let me give you a quick example where that might not be true. And there's always exceptions. So don't be afraid to go out of the box. If you have to give us a call, we'll walk you through some of the expertise that we've gotten over the years. A good example is I did a job for Atlantis Submarine. I don't know if any of you guys are familiar with that. They have submarines, those yellow submarines that go underground and give the tourists a nice look at underwater life. Well, they're charged with batteries. They're actually operated by batteries. So the customer is actually sitting on a fiberglass battery compartment, okay? And underneath their seats are the batteries. Well, there's approximately 1 3/4 inches between the top of the battery and the bottom of the seat. There was absolutely no physical way for that sensor to be pointed down in that application. So we came up with a method to show the customer, Atlantis Sub, how to orient the sensor internally so that the active and the reference bead are at symmetry. They're left and right rather than top and bottom. And therefore, now when he installs it, they mark the sensor, they turn the sensor to the right orientation, and it's been working for them for about 15 years now. So we can do things to get around certain problems, but the rule of thumb is that it should be facing down most of the time. Gas dispersion, this is actually a very complicated subject matter, but, and I'm not sure, I'll be honest with you, I'm not sure many people actually take it into consideration when they set up their sensors. But you should be aware of it from a stand right next to the pump, the beads lasted its 2 to 3 years. Also, compressor stations. We have many units in compressors, and we have a system. I think it's at Walt Disney World in Florida, where they generate their own electricity using turbines. And the original installation, the turbine, they were mounting the sensors in an area where the frequency of the turbine was vibrating the sensor enough that the sensors didn't last as long. They lasted about a year before they gave way. So again, vibration is very important. There are things you can do. You can mount it on rubber mounting feet, rubber housings. You can use anaconda conduit. So instead of rigid conduit, you do flexible conduit so that the vibration coming through the conduit doesn't get transmitted into the enclosure itself. So there are things, and of course, the last thing you do is you just put it in an area that's not vibrating. So. One of the biggest issues that I've seen over the years is improper wiring and grounding. Gas detection being very, very sensitive. If you think of what is happening and what is going on with a gas detector, it's seeing a very, very small signal. And like in the case of GasTel, that signal, that light absorption is being amplified about 1,800 times. So the gain turned up on gas detectors from its signal is huge. Therefore, any little glitch, any little bump, any little electrical or EMI RFI can be amplified as well and give you a system that's not reliable. Grounding is fairly simple. You try to ground at a central location. Most people install a power supply in their electrical room, and then they go out to the sensors from there, and they don't ground the sensors so that you only have one earth ground at one central location, and you don't induce a ground potential. That's probably one of the biggest problems I've seen out there, is where they've grounded at 1,000 feet out at the sensor, they've grounded at the power supply, and then they have 2 or 3 volts AC going across the conduit line that gets induced right into the DC wiring. So just keep in mind that grounding, if you read the manual and you have a good electrician do the installation, grounding could be a problem. We go a little bit, we talked about air current before, but I did this as a separate unit just because I wanted to show you the splash guard on a GasTel, and I wanted to emphasize the fact that airspeed is very important. A lot of times we tell customers to put the sensor on the side of an I-beam or a VAT that has less wind currents. Offshore, if you put this on an offshore application, there's always going to be mostly onshore breezes. So you might want to look into that to determine what the best location for a specific sensor is. The idea of the sensor is you want to catch any leak. By putting a sensor out in the wind that never is going to see high concentrations of a gas is just a waste of time, a waste of money, a waste of maintenance, everything. So airspeed is extremely important. And one of the things that the foam splash guard does, especially for a catalytic bead sensor, is it prevents that high wind giving erroneous readings by cooling off the catalytic bead. So the original foam splash guard was originally designed for preventing air currents or high-speed air currents on the catalytic bead, but of course it's used in so many other areas now that we put it on all our sensors. Continue to talk about the foam winds splash guard. You can see that there's dust, there's rain, there's water, ice, aerosol sprays you got to be careful of. Where I've seen a lot of our sensors out in the field that are painted. People, especially you get a contractor come in and he has no idea what that device is, and he just spray paints right over it, and then of course until the next calibration, nobody knows that they have no gas detection, because the gas detector is only as good as its capability of having gas diffuse across that flame arrestor. So that's almost common sense. And of course, again, we go back to the foam splash guard. By putting that foam splash guard, you prevent the rain, the wind, the snow, the dust, the spray paint, water droplets from ever getting to the flame arrestor. So it's a real good thing to always sell one, indoors and outdoors, with every gas detector that you sell.
Scott, one of the questions came up during the meeting with the electrochem O2 sensor. Being in an environment that has 20% oxygen, is that going to expedite or shorten the life of the sensor?
Okay, let me answer that in two ways. Anytime you have the gas that is being sensed by the cell, you're consuming the cell. However, with oxygen, that was taken into consideration during the manufacturing and the design of the electrochemical cell. So when we sell an oxygen cell, we expect it with 21% oxygen as its norm. We expect it to last 2 to 3 years. So that's going to be opposite. Let's say you have an application where you only have 14% oxygen most of the time. Well, in that case, that cell probably lasts you a little bit longer than in the normal application where it's going to see 21.
That's great. Let's understand that.
Okay, so you're all free to talk. Try not to do it all the time. I hope that answered a lot of your questions and also gave you a good insight on gas fundamentals. I'm always here, and Rob's here some of the time, but he's always available to be called on his cell phone. Beauty of cell phones is we're never out of the office. Anyway, if you have any questions, you need help, please don't hesitate to call us. I walk through a lot of applications, questions with engineers. I have a lot of calls from reps that are at a customer site that have questions that they can't answer or don't want to answer. You can call me right at your customer site, and I'll be available to answer your questions.
Thanks, Scott. That was fantastic. Are there any other questions? I know we put this up for an hour and a half. We were figuring about an hour and 15. We went a little bit over, but here for anybody who has questions.
This is Kevin Conrad with Alesco. I've got a couple questions.
Hey, Kevin, go ahead.
One of the things I'd like to see from Delphian and from Rob, or from Scott, is a competition analysis and why, a lot of these guys use optical mirrors in the IR and talk about how they don't use the heat conduit, heat flow effect, and they kind of down that. So I'd like to know what's the advantages of our heat pump idea and using the gold side versus the actual mirror. Also, what about open path? Something that Delphian, that's a two-part question.
Yeah, okay, let me answer the first one. First of all, the competition out there, look, over the years, everybody learns the same thing. If you actually look at a catalytic bead, it was started in the 70s by one company, and the engineers from that company quit that company and opened up their own company. And then those engineers eventually went on, and before you knew it, you evolved to 10, 15 different companies, all using the exact same technology. Now, over the years, everybody's learned a lesson in their own field. Some catalytic beads were better designed for mining applications, which high vibration. Some were designed mostly for methane applications, and everybody went their own way. As far as our competition with IR, when the IR first came out, there was a lot of different technological ways to do infrared detection. There was choppers, there was mechanical motors, there was encoders, there was tuning forks. Those were all ways to get your light on, light off. Well, a lot of people had problems with that because the people who used motors to get their light on and light off learned that the motors burned out in a year and a half. And the ones who used frequency choppers like tuning forks to get your light on, light off, they learned that eventually the tuning forks wore out and cracked. Coming in a little bit later than some of our competition, we learned all this stuff and said, but by actually using electronics to blink your light on and off, we got rid of all the mechanics that could fail. And we could blink a light on and off for 50 years electronically without anything wearing out. We also learned that some of the speed of response issues by our competitors were due because once the gas permeates across the flame arrestor, it has nowhere to go quickly. So by increasing the heat flow inside the chamber, we created the chimney effect. We didn't make that up. I mean, that's how your flue in your hot water heater works. Hot air rises up the flue. So we took what we knew and we designed a better detector. So when it comes to our competitors, I remember one instance real quickly that one of our big competitors, their first 25 IRs at one of the companies that we now have our IR detection at, in their first change of seasons, the silver actually started peeling off the back of their mirrors. And when that happened, they lost all gas detection. And so their second design is they removed the mirrors. We did it a little differently. We actually do flashing of gold over a nickel plated plastic. Therefore, we now don't have any method of peeling. There's no way the gold can peel off. It's you know, it's like a gold ring. It eliminated that whole problem that some of our competition had. And of course, with mirrors, you have to focus the mirrors. You have to adjust them so their reflection is perfectly set up. So we learned over the years a lot of new tricks that the original IR manufacturers had to learn the hard way. Going to your second question real quickly, open path is a whole different animal. I am not a big believer in open path for a whole bunch of reasons. A couple of the ones on my mind is, number one, if your open path goes down, you have zero gas detection. So you might have an open path that does the job of 20 gas detectors, single point gas detectors. In 20 detectors, if one goes down, you have 19 left. In an open path, one goes down, you have zero detection. Number two, when you look at open path, the only thing open path can do is say, do I see gas or don't I see gas? Its accuracy is nil. And the reason I say that is because if you have a very high gas leak, let's say you have an open path looking at 300 foot span, okay? If you have a gas leak right in the middle that's 1 foot wide and it's a big leak, that IR, that open path is going to say you have 10%, an average of 10% LEL over the 300 feet, okay? Now, if you have a big leak and it's 5% LEL cloud over the entire 300 feet of detection, it's going to turn around and say, you got 90% LEL per meter leak. So it has no way of knowing how far across that entire 300 feet the leak is. So open path was really designed for go, no go. It's a great thing for maybe a platform or a company that doesn't expect to see gas. And if it does, wants to react to it, doesn't really care how forward. So you go into a customer and you say, what are you trying to look for? And the customer says, I need to monitor hydrogen. Well, immediately, as a rep and as a manufacturer, I can tell you exactly what products we sell that can be used to monitor hydrogen. It would be the catalytic bead, and the SafeCal is a group A, B, C, D enclosure. It's designed to see hydrogen. If the customer says, I need to monitor natural gas, well, I just need to supply them with something that can see natural gas and has a group D rating. So that would be my 550 sensor, that would be my IR sensor, that would be my gas cell sensor. So you basically choose what you need rather than telling them what you have and let him fit it into that. So I go usually the opposite way. I always ask the customer what he needs and then tell him what we have to meet his needs. Group C and D are all those chemicals that you see in that chart. And the reason is because when they explode, when they ignite, the pressure of the ignition, the pressure of that explosion is such that group D is not as powerful as group C, which is not as powerful as group B. And of course, the biggest explosion out of all of them is acetylene. If you've ever seen acetylene ignite, it ignites with such power that you need to encapsulate it in an enclosure that could withstand like 600 PSI because it's got so much pressure created from the flame. How do I think we...
Are there any other questions? Joyce, you had that first question about the oxygen. Are you comfortable with the oxygen answer on the electrochem?
Yeah, I'm good. Thanks for the information.
Oh,
Also,
my
I
pleasure.
just wondered if we could get a copy of the presentation after the fact.
I'm going to go ahead and send the presentation out to everybody.
Perfect.
Any other questions? All right. We hope the webinar was helpful. What we're trying to do is to just get everybody's education level up a little bit higher. We hope that we accomplish that today. And Scott and I plan to do a few others for the rest of the year, every few months, just to get one more out there. And we're probably going to do gas tail next. But thank you again for attending. I know that it's expensive for us all to not be out in front of customer and talking to customers, and appreciate it. If there's no other questions, we're just going to end the meeting.
Thank you, Rob.
Yeah, thank you, guys.
Thanks, guys.
Thanks, Rob. See you.
All right, take care now.
Yeah.